So again, so this is when G is planar. So now you start using planarity. So we'd like to have some qualitative understanding of what happens to these probability measures in some large-scale limit. So it's not entirely clear, what kind of properties you look at large scale, because, you just have a bunch of combinatorial ways of putting edges. So we'd like to kind of understand how to make a macroscopic object out of this microscopic data. So that goes to first hand with quite a distinct point of view. So now I'm going to be even more specific. So I started with graphs with an even number of edges, and then planar graphs. So now I want bipartite and planar graphs. So a bipartite graph is just a graph in which you have a proper two-coloring of vertices. So you can color half of vertices in black and half of vertices in white, such that any neighbor of a black vertex is white and vice versa. Another way of phrasing the condition is that you look at faces, and you want all faces to have even degree. Okay, so maybe I've got something like so I color just my graph with two colors. So these are conceptually, these are two distinct colors. Okay, so you can define the height function in this, or you have several reasonable definitions of the height function in this framework. So I'm going to be a bit more specific for simplicity. So I'm going to describe a particular way of getting bipartite graphs. So you take a rhombus styling of the plane or a portion of the plane. Okay, so it doesn't look like a very generic styling. Okay, so these are supposed to be rhombi. So all edges have the same length, delta. Okay, so it's it's bipartite, but that's not quite the graph I want. Okay, so I just pick my vertices of two types, so depending on parity. So that's the first step. And then I'm going to add new vertices in the center of each face. So now I've got not only a graph, but I have also a rigid embedding in the plane. So these are, okay. So I'm adding a new vertex, which is now white inside each face. Okay, and then I've got a new graph whose edges are well, red. Okay. So this red graph is bipartite. So it has white vertices and black vertices themselves are split into two subtypes, which well. So I'm going to look at perfect matchings on this graph. So I'm not. Okay, so now I promised I was going to define some height. So I'm going to define the height. Oh, so that's actually the same. So the height is going to be defined on the midpoint of each edge of my original rhombus tiling. Okay, so now this is going to be defined by a local rule depending on a matching of M. Okay, so you have a matching of M, and I'm going to look at the local picture. So the local picture is more or less always the same. Yeah. So if you look at a generic white vertex, you see 4 black vertices around. And it's in the middle of 2 orthogonal edges. Okay, so now I've got the midpoints of the original rhombi edges, which are located in this direction. And I've got, in my matching, I know that the white vertex is matched to exactly one of its 4 neighbors. Okay, so that's, so M, capital M is a fixed graph, and then I've got a kind of random matching, small m. Okay, so now the rule is going to be the following. So you've got angle. So again, I'm not looking at an abstract graph anymore, so it's really embedded in the plane. So I'm looking at the angle between these 2 points seen from the white vertex. So if the height is some value h naught, some base value h naught at this point, I'm just going to add the angle to obtain the height at this point. And then same thing when I go around the white vertex. So of course I cannot do it all around the white vertex because then I'm going to get contradiction. I mean, I'm going to go up by 2 pi, but I'm given a breaking edge in my matching. So this is going to be valid except when you get a matching where you go up by the angle and then down by 2 pi. So that's the local rule around a white vertex. And then the local rule around a black vertex is the same with opposite orientation. So now, because of the geometry of the embedding, if you look at the angle between these 2 points seen from the white guy, it's the same as the angle between these 2 points seen from the black guy. So if you look, if you want to look at the jump of height between these 2 points, and if you use the rule around the white vertex and the rule around the black vertex, you get the same answer. So this shows that the height function is going to be well defined once you set the base value somewhere. if your graph is embedded in, say, a simply connected surface or something like that. Okay. So now you can have a sequence of graphs, and then you're going to have a sequence of height functions. So if on each graph you sample a dimer from your dimer measure over there, you get a random height function, and then you get a sequence of random height functions, and then you can start thinking about scaling limits. So let me describe first some results of Kenyon. So you can, just for simplicity, so it's not. It's not so important. So you can look at this question on the square lattice. So the square lattice is certainly one of these semi-exotic lattices. So if you keep track of what's going on, the height function now is defined in the center of each of these faces. Okay, so I'm going to take a simply connected domain D, and then I'm going to put on this simply connected domain a square lattice with small mesh delta. I'm not going to discuss boundary conditions, which are of crucial importance, but you can handle them. So for well-chosen boundary conditions, you can do the following thing. So for each delta, you look at your graph, and then you sample a dimer configuration, and then you look at the height function which you compute from this dimer configuration. So now these guys don't have the same kind of state space because each of them is defined on the dual of a different graph and so on. So you can do kind of crude thing and just extend this function in a piecewise constant fashion in each face. So you decide that the value of the height inside each face is constant and equal to the value in the center. Okay, so now you have a sequence of probability distributions on a single space, which is a space of, say, piecewise constant functions on D. So it's not like a grid space, but at least it's a single state space. So in this framework, you can prove convergence in the sense, I would like to say, of finite dimensional marginals. So let me just first point out that in this picture, you let delta go to 0, but the values are not scaled. So if you think of a typical invariance principle, like Donskian invariance principle, so you scale time and height for random walks, for simple random walks, and it converges to Brownian motion. So here, in a sense, we scale space because, I mean, D is fixed and you let the mesh go to 0, so that's what we expect, but the values we don't scale. So in particular, in the square lattice, you just move by pi over 2. So the jumps are always plus or minus pi over 2. So all values of these guys belong to a discrete lattice, but still we're not scaling. So what you can do is okay, at this scale, at this level, it doesn't really make sense to try to get sharp results. So you just take a test function, so a smooth function with compact support in D. And you integrate your piecewise constant height function against this test function. So now you have a sequence of simply random variables. So this converges as the mesh goes to 0 to a normal variable. Yeah. I'm just going to subtract the mean. I mean, you can take care of the mean, but for simplicity, I'm just going to center the variable. So you can prove that the mean converges too, so that's not a big restriction. So once you center, this goes to a normal variable, so with 0 mean, and with variance, so you got a constant which depends on the, which depends on the basically normalization of your height function. So it's universal in the sense that if you change your lattice, your underlying lattice, you get the same constant. And it's explicit, but I don't really remember from top of my head. So the important thing is that this depends on your test function in the following way. So you take the test function, and then you invert the Laplacian with Dirichlet boundary conditions, and you take this thing. So this is the quadratic forms on these test functions. So you can write slightly more explicitly as the integral of psi against the covariance kernel, which is just the green kernel for the Laplacian with Dirichlet boundary conditions in D. Okay. So now you'd like to have basically a single limiting object, because I start from a height function which lives in this big vector space of piecewise constant function, and then I just project on a one-dimensional marginal and take limits. So of course, because of general results on Gaussian limits, if you know it for each test function, you know it for finitely many test functions. So that's true if you take the joint distribution of the phi of the height function against finitely many test function, you'll get a joint distribution where instead of having the same guy, I mean the covariance kernel, you take certain number of test function psi I and psi j, and you'll get this covariance kernel. But that's really not any generalities added there. Okay, so if you ask the question in this fashion, so what would be a limiting object which has the property that when you test it against a smooth function, you get this expression? Okay, so I mean it's an element of a vector space. I mean the question is twofold. So you want first to find the vector space and then the distribution on the vector space, such that this is satisfied. So when you integrate h against a test function, you get always a normal variable with the proper variance. So one way of doing it is the following. So h is something you can integrate against smooth functions, so basically it's a distribution. So now the space of all distribution is some Frechet space, so it's not red, but you can look at something a bit more specific. So you look at Sobolev spaces. Okay, so now you want the Sobolev space to be large enough, so you take say, a negative index sobre F space, so something which is slightly larger than L2. In particular, has no pointwise values, but still. So if you look at this as an abstract Wiener space, you can find a Gaussian distribution on this abstract Wiener space such that this is satisfied. So kind of more explicitly, so if you take so if you take a Hilbert basis of H1, so if you look at all smooth functions with compact support, you can put a Hilbert norm on this space in this way. And then you take the closure, you get a nice Hilbert space, H10 of D. So you take any Hilbert basis of this Hilbert space. So you take an IAD sequence of standard normal variables, and you look at this series of functions. So this is certainly not going to be convergent in this guy, but if you extend the space enough, you can make it convergent. So this is going to converge almost surely in any negative index over F space. So the upshot is that this, you can have a well-defined object in a well-defined abstract Wiener space, so a Banach space of distributions, such that this is satisfied. And I also claim that you get better, you can get better than a finite dimensional marginal, you can get a functional CLT. So by mapping all these guys, instead looking them as random elements of your Wiener space, and then you get a sequence of probability measures on some Polish space, and then you can take limits, and then this is going to converge to this Gaussian distribution. Okay. So I've just stated the result, so now I'd like to explain a bit how to think of these things and how to take limits. Okay, so I'm going to discuss this in terms of Cauchy-Riemann operators. So first, the very good thing about Castellan result is that it's valid for all choice of weights. Okay, so if you fix the planar graph, you can modify the weights, and then you modify the Castellan matrix, and you can still compute the weighted partition function or modified partition function. So in this, so I'm going to use this in the following way. So let me take a smooth one form or 0-1 form. So something which is basically a version of my test function. So which is going to be defined, say, inside D. And I'm going to modify my basic Castellan matrix K in a multiplicative way. So if you think of your lattice as having mesh delta, you multiply your basic weight which takes care of orientations and everything by the integral of your test form on an edge. So it's something which is of order 1 plus big O of delta. So it's a multiplicative perturbation of your Castellan matrix. And then simply using Castellan's result for these two weightings, so the basic weighting and the modified weighting, you see that the ratio of these determinants computes the expected value under the basic matching measure of basically the characteristic functional of H. So if you integrate H against D of alpha, so D of alpha is a two form, H is a function, you can integrate once against the other. So if you keep track of things, basically you're computing the full characteristic functional of your field by this ratio of determinants. So clearly, if you can take limits of this for all alpha, this characterizes the limit of the field, if you have tightness, but you can get tightness. So it's not quite true, but you can make it true if you work a bit harder. So basically, the issue that we have is to find the limit as delta go to 0 of the ratio of these two determinants. So it's important to look at the ratio because, each of them, you won't be able to get sharp enough asymptotics because, the boundary is kind of arbitrary, for instance, and that makes the asymptotic of each of these guys very complex. But the ratio is kind of better behaved. So in a sense, what we need to do is simply to take the ratio of determinants to the limit. So I'm going to proceed a bit in a different way by first taking the operators to the limit and then look at the determinants of the limit. So is this. Okay, so again, I'm going to just look at the local situation. Yeah, I skipped something at some point, but so I just tested the result for general graphs, where you get the Pfaffian of your Castellan matrix. So now if your graph is bipartite, what you can do is write your matrix in block form. So you first list all black vertices, then all white vertices, and so on. And since you cannot have two neighboring black vertices, you get zeros on the diagonal blocks. Since your matrix is anti-symmetric, the two blocks are, some matrix and minus its transpose. So if you take the determinant of K, it's equal to the determinant of this block squared. So the partition function is just the determinant of one of these blocks.
Is the lattice periodic?
No, at this point, lattice is, no, it's actually...
Then you don't know how to compute the right? Well, you don't know eigenvalues.
No, you don't know eigenvalues. But again, I'm not computing a single determinant. I'm computing a ratio of a perturbation divided by a base determinant. Okay, so I claim that you've got to put a Castellan orientation on this thing. So I claim that this is going to give you a Castellan orientation. So you take an orientation of your first type black vertices, and then you rotate, and this gives you an orientation on the second type black vertices. And this is going to be a Castellan orientation. I don't want to put maybe exact weights, but yeah, maybe I'm going just to do for the square lattice. So the Castelline coefficients, so the coefficients of the Castelline matrices corresponding to this picture are as follows. So now I'm just going to, maybe for clarity, by conjugating your Castelline matrix with a matrix which is 1 for type 1 and I for type 2, you get new weights which are -1, -I, 1, and plus I. Okay, so imagine that the mesh is delta, and you have an operator that takes functions which are defined on black vertices and map them to a function which is defined on white vertices. So imagine that the function which is defined on black vertices is actually a smooth function which is defined everywhere in D, and which you just restrict to black vertices. So if you evaluate at the white vertex this function, what you get is the value on the right vertex minus the value on the left vertex plus I times the value on the top vertex minus the value on the bottom vertex. So this is basically up to constant. If you just do a Taylor expansion, this is just the operator D over dz bar. Okay, so you can think of the Castelline matrix as a finite difference version of D over dz bar. Okay, of course, I could have used a different weight change and exchange plus I and minus I, and then I would get a discrete different version of D over dz. So in a sense, it's as much D over dz bar as it is D over dz. But let's think of it as D over dz bar. And now if you look at this perturbation, so if you use this one form to make a perturbation of this thing, what you get is again, in the sense of finite difference operator, D over dz bar plus a term of degree 0, so A times F. So kind of potential, but this is a Cauchy-Riemann operator. Okay, so now we just have so we can think of the Castelline matrix as being a discrete version of D bar, and the modified matrix by generic potential to be a discrete difference version of D bar plus alpha. So now what's next? Well, we have to take determinants. So now these are continuous infinite dimensional operators, and we want to take determinants of them. So so the usual recipe for it is that of zeta determinants. Okay, so let's take I'm going to be a bit wishy-washy, but you can make this completely tight. So yeah, let's take a Laplacian operator or something which looks like the Laplacian, meaning that the symbol is the Laplacian, and then maybe you've got first order and zeroth order terms. So linear differential operator. And let's look at its spectrum. So if everything is okay, then you have a nice spectral decomposition, and you have a sequence, a discrete sequence of eigenvalues that go to infinity. So we know that, well, the determinant is just the product of eigenvalues. Here, I mean, the slight problem is that this is just a sequence that goes to infinity. So more precisely, you've got the while asymptotics that lambda n goes to infinity like a power of n. So 2 over d, or d is 2. And constant is something which depends on the volume of your manifold. Okay, so I guess that's the point where I get in second gear. So you can form a zeta function from this spectrum. So you see that if you had a spectrum that goes to 1 quickly enough, you could just take the product, and then everything will be OK. So here the spectrum goes to infinity, but it goes to infinity in a regular enough fashion so that we can still work something out. So formally, if you take the derivative of this at 0, this is sum of minus log of lambda n. So this is minus log of product of lambda n. So I think, so this is absolutely convergent when the real part of S is large enough. So this is analytic in S in half plane, and this has a meromorphic continuation to C. And in particular, it's holomorphic near 0. So then you define the zeta determinant of your operator as in terms of the derivative at 0 of C. So if this is a finite sum, this is the usual definition. And if it's infinite, well, this gives you an extension of it. Okay, so it's not, it's absolutely not helpful way to, I mean, this is not good for much, but. So you can also define, you have an equivalent formulation. So for this, from this definition, you can go to another version, which is computed in terms of the trace of the id kernel. So this is the id kernel. You take the trace, which consists in integrating the id kernel on the diagonal. So this is the gamma function. So that's basically the way that you get while asymptotics. I mean, you go in this direction, and then you have short-term asymptotic for the id kernel. So that's classical analysis, and then by Abelian-Tauberian arguments, you can go back there. Okay. So what we want is basically not to understand the determinant of a single operator, which actually we don't need, but what happens when we modify the operator. Okay, so let's. Let's discuss variational formulae. So if you have so let's start by something easy. So if you have a one-parameter family of matrices, so a smooth one-parameter family of matrices, you can compute easily the variation of the log determinant. So in terms of, so that's going to be the trace of derivative of your matrix times empty inverse. Okay, so now we'd like to have something similar for Laplacian type operators. So meaning that the symbol is fixed, so it's the symbol of the Laplacian. And then what happens in degree 1 and degree 0, you move smoothly in terms of some parameter t. Okay, and then claim is that d over dt log that okay, so if everything was okay, you would get just the variation, the derivative of the operator with respect to the parameter, composed with the inverse operator, and then you take the trace. Okay, but of course this is something like, this is actually the green kernel, or a version of the green kernel, so it blows up on the diagonal. So you want to compute this on the diagonal, which is exactly where this guy blows up. So you use id kernel regularization. So you just move this by flowing the id kernel for a small time u. So now this is a completely smooth kernel, which you differentiate. And when you apply a degree 1 operator to this smooth kernel, and then you get a nice freedom kernel, and you take the trace by integrating on the diagonal. Okay, now this blows up as u goes to 0. But you just take the limit as u goes to 0, so this is kind of fancy. Fancy limit. So basically, this is going to be a Lorentz theory in your fictitious time parameter u. And you're going simply to pick the coefficient of degree 0 in this Lorentz expansion. Okay, so that's the general variational result. So in particular, okay. So this applies in kind of several situations. So you can get conformal anomaly formula for what happens when you take the Laplacian and then you modify the metric, the Riemannian metric, while staying in the same conformal type. So you get such a formula. So now, okay, so what do we want? So the operators we have, so these Cauchy-Riemann operators, they are basically not Laplacian type, right? They are just degree 1 operators. But you can compose them with their adjoint, and then you get something which is Laplacian plus something in degree 1 plus something in degree 0. And then you take your test potentials, and then you move across a family of test potentials. And you want to understand this variation. And if you apply this formula, you get some formula telling you, well, you look at the diagonal, and then you take the id kernel. So now if you think of what the id kernel is doing, basically to first order, you just take uniform direction, and then you integrate over a small circle. I mean, you average over a small circle. So if you So if you look at what these operators look like, so this is a modification of d bar. So if you look at the inverting kernel, it's going to look like, say, 1 over. So if you fix W and you look at B close to W, which is what we need to do, we need to look at what happens near the diagonal, you get a leading term, which will be 1 over B minus W, and then a constant and some subleading terms. And then, okay, so you got some correction which you can take care of. And now if you look, so this guy is going to average out, and then you're going to pick out the constant term. And this is the one you need for the variational formula. So now, I mean, the analytic claim I'm making is the following. So if you take the inverse of your modified Castellane matrix, and you subtract the leading term, which is kind of oscillatory, so it's going to average out exactly, this converges to the same thing. So, but I mean, you subtract a different oscillatory term. So we've got some discrete oscillation which cancels out, and then you get some continuous oscillation which cancels out. So these are two different guys. But once you get rid of these two guys, you get the same significant basically coefficient. And this is more or less enough to ensure convergence. Okay, so maybe maybe very briefly, so you can get more kind of more precise results in the following. So, for instance, in the following way. So, if you take two mark points in your domain. So we know that well, I mean, maybe that's not exactly what I want to. So if you take 2 points in your domain, if you look at the height function at each of these points, because of the lattice constraints, It's equal to a constant depending on parity or something, plus an element of the lattice 2 pi z. So in this Gaussian invariance principle, we don't see at all the lattice constraint, so it has completely disappeared. So there are several ways to make it reappear and have something which is kind of more significant. So one is the following. So you can look at the, say, I difference. For normalization, it's kind of convenient. And you put a parameter sigma in front. So that's a random variable, and then you take the average of this random variable when you take all possible matchings. So this is so this is a random variable whose variance is of order log of delta. So you take a kind of spread out lattice valued random variable, and then you put this guy in front. So clearly this is going to go to 0. But you'd like to quantify this. And equally clearly, this is one periodic in sigma. Okay, because of this condition. Okay, so now if you're like very optimistic about the Gaussian free field limit, you say that H, maybe let me put deltas. So if you replace your discrete lattice valued field by a continuous field, so you take the continuous free field and you take the average on a microscopic phase. Okay, so that's a well-defined quantity. So yeah, let me call this H naught of X. So if you're like really optimistic and think that the invariance principle is valid at all scales, even if at this scale clearly, I mean, you have a discrete, completely discrete valued object and a continuous object. So you think that this is asymptotic to E I sigma H naught X minus H naught 1. So this depends on delta because of this averaging. So this is the average on the face of size delta. So you can compute, this is very simple Gaussian computation to compute. So this is taken against free field. So it's a very simple Gaussian computation to compute this. So because you have this log, this is going to be something like exponential of constant time log delta. So this is delta to some power. Yeah, I mean, sigma is a different sigma than before, but okay. So the asymptotic will be of type some power of delta, which is quadratic in sigma, times some function depending on the position of parameters. So this is patently false because right-hand side is not periodic in sigma. So there's a conflict between the lattice constraint and now the scalar limit. So the claim is actually going to be valid for sigma between -1 alpha and E alpha. Okay, which is kind of the maximal span on which this can be valid without like obvious contradiction. Okay, so I guess that's a good place to stop. Okay, so G is yeah. I mean, well, I mean no, because you've got boundary, right? So if it's in, if it's in I mean, the full plane version of this, yeah, it's I mean, it's a trivial function of x, y in the full plane. I mean, this is basically the green kernel between x and y. So in the plane, the green kernel is log of x minus 1. So we take exponential, yeah, it's x minus y to some power, yeah. Yeah.
So when you write trace or into the minus u and things like that, is there a way to interpret this in terms of preservation of the geometry of the underlying process?
Well, I mean, yeah, I mean, I could, yeah. So there are different ways you can do this. So I could go on. So basically, you have somewhere, yeah, so you start from d bar, and you think of, I mean, you look at d bar as operating on the trivial line bundle. So you have trivial line bundle with a trivial Hermitian metric. So then you have different ways of doing perturbations of it. So one way is to modify the complex structure of the line bundle. So for instance, if you're on a torus, if you start twisting the line bundle, then you're going to compute the winding of the field, which is going to be this kind of discrete type object. So it's a bit simpler than this, but that's you get when you modify the complex structure. And you can also modify the metric of the bundle. So it's a line bundle. You have, the metric on the line bundle, which is compatible with the underlying complex metric. You can still vary by basically varying the norm, and that's going to give you the fluctuation of the field. Yeah. So now, I mean, the underlying geometry is fixed, but you look at, you play with line bundles above the underlying geometry. Yeah.